So the next thing that we're going to cover in class, guys, is what's called rotational dynamics. So when we talk about dynamics, we talk about a change in things. So as opposed to statics, where we talk about things that remain the same over time. So rotational dynamics is looking at the change in rotational motion of an object. So how we can change its rotational motion. And when we think back to how we studied linear motion, we had this equation: force, net force, is equal to the mass of the object times its acceleration. So we have Newton's second law here. And so this is the formulation of the second law for what's called translational motion. Okay, so motion along lines, or, as a parabola or whatever. So this is the second law. It should come as no surprise to you that there's an equivalent expression for rotational motion, because this tells us how we can cause acceleration. So acceleration is a change in translational motion, it's a change in velocity. And what this says is that we have to apply a net force in order to cause acceleration. And for rotational motion, the equation says that we have to provide a net torque. So this net torque would be the sum of the counterclockwise torque minus the sum of the clockwise torques. Okay, so if we have an object and we have torques being applied to the object, we take the difference between the sum of the clockwise and counterclockwise. And if there is a net torque, then that will cause some angular acceleration. And so we saw this before when we were dealing with rotational kinematics. Acceleration. Okay, so this angular acceleration is in radians per second squared. Okay, and so the question is, okay, so far so good. What takes the place of the mass? And this is where it gets a little weird. What takes the place of the mass in the equation is something called the rotational inertia. Okay, rotational inertia. And this rotational inertia will be different for different objects, and it depends on their shape as well as their mass. So what the units of rotational inertia will be kilograms, which is the unit of mass, times meters squared. And so that meters squared, and see where it comes out, we have to look at the different equations for rotational inertia that different shaped objects have, which we'll get to in just a sec. But this equation, this is the kind of the second law equivalent for rotational motion. A net torque will produce an angular acceleration, and it has this constant of proportionality called the rotational inertia. And a lot of times rotational inertia is defined as the rotational mass of the object. And so, if you look at the units, this will be Newton meters. As I said, this is kilogram meters squared. This is radians per second squared. So on this side, we'll have a kilogram meter per second squared times a meter, and that's a Newton meter. I just want to prove to you guys that, that these two sides are equivalent as far as units go. So rotational inertia. You guys don't have to memorize this table. You might want to take a screenshot and print it out and paste it in your notebook or something, because what these give you are the different equations for the different shaped objects and how to calculate their rotational inertia and how to express it. So this M would be the mass of the object in kilograms, and the R is the radius, if it's applicable. So it's the radius of the object. Sometimes you'll see an L, and they're talking about, the length of the object. So different objects, you have to think, if you're given a problem, you have to think, okay, what's the shape as well as the mass, and then you got to pick out the appropriate equation. And we'll practice doing that probably next week. But what we're going to do before that is we're going to be doing a lab. So I wanted to make this video for you guys so you have some context, but we're going to be doing a lab in the next couple of classes that will look at this relationship between torque and acceleration. And then it's also going to look at rotational inertia and how different, we'll call it distribution of masses or different shapes, have different rotational inertias. So that's what we're doing for the next couple of days. And then after that, we'll think about some problems and how we can apply this in more of a problem setting. So if you guys have any questions about this, feel free to ask me in class, and I'll see you then.